Hello, welcome to this video on the design of laterally restrained beams as per Eurocode 3. So before presentation, let me introduce myself. My name is Jarajan P. Currently, I am working as a faculty in the Department of Civil Engineering in an institute of national repute. So basically, I am a structural engineer having strong background in geotechnical engineering, having 20 years of experience in the design of steel and concrete structures built in various industrial facilities like refineries, petrochemicals, and power plants. Currently, I am in the process of making a series of video presentations that covers the design of various structural components like beams, columns, plate girders, and base plates. This presentation shall be considered as the first one in this series. So, let us proceed. I am very optimistic that this presentation will benefit two groups of audience. The first group representing the students pursuing their UG or PG programs in civil and structural engineering. The second group belongs to the practicing structural engineers involved in the detailed engineering of steel structures using EC3. The reference documents used in this presentation include EN 1993-1-1 2005 Eurocode 3 Design of Steel Structures Part 1-1. This is all about the general rules and rules for buildings. The second document is EN 1993-15 2006 Eurocode 3 Design of Steel Structures Part 1-5 General Rules Plated Structural Elements. So it is expected that both the students and the engineers have a copy of both these documents while going through this presentation. So this presentation is all about the design of laterally supported beams that have their flanges restrained against flexure buckling. Now, how to restrain a flange so that flexure buckling is avoided? This is normally done in two ways. Either I will provide a plan bracing, or I'll make use of an RCC construction that will restrain the flanges against the buckling. So the contents of this presentation include: number one, various guidelines in the reference documents concerning the design of laterally restrained beams, and at the end an example problem is solved for a better interpretation of these guidelines. So let us get back to work. Many of the criteria given in this presentation are taken from the first document, EN 1993-1-1. So let us go through this criteria first. The use of correct material properties is an essential part in the design of any structural component. The properties relevant to the strength design of steel members include the yield strength Fy and the ultimate strength Fu. Table 3.1 of Eurocode provides you the Fy and Fu values. Here I have reproduced a part print of table 3.1 below. As you can see, the first column provides you the various steel grades starting from S235 to S450, and the other columns provide you the values of Fy and Fu depending on the nominal thickness of the various elements. Please note down two things. The first one is, in the steel grade S235, the number 235 indicates the yield strength, and secondly, the yield strength also depends upon the nominal thickness of the member. As you can see, for thickness less than 40 mm for S235, Fy is 235, and for thickness between 40 mm and 80 mm, it is reduced to 250 Nm square. In addition to material properties such as Fy and Fu, Clause 3.2.61 of the code also provides you material coefficients like the modulus of elasticity E, shear modulus G, Poisson's ratio nu, and the coefficient of linear thermal expansion alpha. As per this clause, E shall be taken as 2.1 into 10 raised to 5 Newton per mm square. The value of G shall be obtained using the standard equation G equal to E divided by 2 into 1 plus mu, and this shall be equal to 8.1 into 10 raised to 4 Newton per mm square. The Poisson's ratio nu shall be taken as 0.3, and the value of alpha is equal to 12 into 10 raised to minus 6 per Kelvin. So let us discuss about the classification of cross sections. We know that steel beams are made up of components like the flanges and webs, which are very slender, and there is every possibility that the beam capacity is limited by the local buckling of these components. The basic objective of the classification of cross-section is to identify the extent to which the resistance and rotation capacity of the cross-sections is limited by its local buckling resistance. Clause 5.5.2 of the code identifies 4 classes of cross-sections based on the extent to which local buckling will affect the capacity of the beam section. Class 1 of cross-sections are those which can form a plastic hinge with rotation capacity required from plastic analysis without a reduction of the resistance. Class 2 cross-sections are those in which the plastic moment of resistance could be developed, but they have limited rotation capacity because of the local buckling. Class 3 cross-sections are those in which the stress in the extreme compression fiber of the steel member, assuming an elastic distribution of stresses, can reach the yield strength, but local buckling is liable to prevent the development of plastic moment of resistance. Class 4 cross-sections are those in which local buckling will occur before the attainment of yield stress in one or more parts of the cross-section. So to summarize, while class 1 and 2 can develop their plastic moment of resistance, class 3 and 4 will be able to develop stresses in the extreme fiber equal to the yield stress. So now the question is how to classify a cross-section. Clause 5.5.2 of the code will provide you the limiting proportions to help you to identify a particular cross-section and classify it either under 1, 2, 3 or 4. Please note that a cross-section is classified based on the classification assigned to its component like the flange and the web. A part of table 5.2 is reproduced in the presentation. As you can see, for example, for class 1, for a flange that is subjected to compression, the C/T ratio should be less than or equal to 9 into epsilon, where C is the outstand of the flange. Accordingly, you can make a classification of the entire cross-section for both the flange as well as for the web. Having done the section classification, now is the time to perform the capacity verification of the beam cross-section. Clause 6.2.5 of the code provides you the criteria to perform the verification for bending moment. As per this clause, the design value of the bending moment MED at each cross-section shall satisfy the criteria MED divided by MCRD to be less than or equal to 1, where MCRD is defined as the design resistance for bending calculated as follows. Please remember the value of MCRD depends upon the classification of the sections we made earlier. For example, for class 1 or 2 cross-sections, MCRD is equal to MPLRD, that's equal to WPL into Fy by gamma MO, indicating that the section is fully plasticized. Whereas you can see that for class 4 sections, MCRD is calculated as W effective minimum into Fy by gamma MO, indicating that only the extra fibers are subjected to the yield stress. So let us see the verification for shear. Course 6.2.6 of EC3 provides you the guidelines for verification against shear. As per this course, the design value of the shear force VED at each cross section shall satisfy VED divided by BCRD should be less than or equal to 1, where BCRD is equal to the design plastic shear resistance VPLRD calculated as VPLRD is equal to AV into Fy by root 3, this divided by gamma MO. Here AV represents the shear area which shall be computed as per 6.2.63 of the code. In the case of deep girders, it is possible that the shear failure is associated with the buckling. Accordingly, for webs without intermediate stiffness, its capacity shall be verified as per section 5 of EN 199315 if HW by TW is greater than 72 into epsilon by eta, where the factor eta may be conservatively taken equal to 1.0. So in the previous slides, though the verification for bending and shear are carried out independently, clause 6.2.81 of the code says, where the shear force is present, suitable allowance should be made for its effect on the moment of resistance, which is reflected in clause 6.2.82, according to which, where the shear force is less than half the plastic shear resistance, its effect on the moment of resistance may be neglected, except where shear buckling reduces the section resistance. Otherwise, as per clause 6.283, a reduced moment of resistance shall be taken as the design resistance, which shall be computed based on a reduced yield strength, given by 1 minus rho into Fy, where the factor rho shall be computed based on the design shear force and the plastic shear resistance as rho equal to 2 into VED by VPLRD minus 1 the whole square. Having verified the capacity requirements for the bending and shear force, we need to finally perform the verification concerning the serviceability limit state SLS. As per clause 7 of EN 1993-1-1, a steel structure should be designed and constructed such that all relevant serviceability criteria are satisfied. It shall be noted that EN 1993-1-1 do not provide any specific requirements regarding SLS. Accordingly, the verification shall be done as per the values of the criteria provided in the project documents. For example, in the case of beams supporting brittle finishes, normally we use a limiting deflection of a span by 360 for the verification of SLS. So, we have gone through various criteria given in the document EN 1993-1-1 to help us assessing the capacity of sections for bending moment, for shear failure, for the buckling capacity, etc. Now we should go through an important criteria set out in the document EN 1993-1-5. For verification of web transverse forces, clause 6.12 of the document considers three modes of load application. First one, as shown in the first sketch, through the flange and resisted by shear forces in the web. And as shown in the second sketch, the load is applied through one flange and it is transferred through the web directly to the other flange. And as shown in the third sketch, the load is applied through one flange adjacent to an unstiffened edge. So in our case, when a beam is supported over a finite length of the bearing SS, case 3 is very relevant. So clause 6.2 of the document provides us the design resistance of the web to local buckling under transverse forces, which is calculated as FRD is equal to FYW into L effective into TW divided by gamma M1. The equation for FRD, we know that we have our parameters except L effective, where L effective is the effective length for resistance to transverse forces, and this is calculated as per clause 6.12 as L effective is equal to psi f into Ly, where Ly is the effective loaded length and psi f is the reduction due to local buckling. So the computation of L effective consists of a number of small calculations. So first we need to calculate Ly, and if you want to calculate Ly, you need to first evaluate Le. So please remember Le is equal to Kf into TW square divided by 2 FYW into HW, which should be less than or equal to SS plus C. Remember, SS is the length of the bearing and C is the location of the bearing from the free end of the beam. And Kf is calculated as 2 plus 6 into SS plus C divided by HW, and it should be less than or equal to 6. Having computed the Le, now we can go for the computation of Ly. Clause 6.53 says Ly shall be taken as the smallest of the following, that is Ly is equal to Le plus square root of m1 by 2 plus of Le by Tf the whole square plus m2. That's the first equation for Ly. And the second equation is Ly equal to Le plus of Tf into square root of m1 plus m2. Please remember that all the expressions given in this presentation for Ly and L effective are applicable only for the third case, wherein the load is transferred to one flange adjacent to an unstiffened end. For computation of the effective length L effective, we require the parameters M1 and M2, which shall be calculated as per the equations given in clause 6.51. The value of parameter M1 is given by M1 equal to Fyf into Bf divided by Fyw into Tw. Remember that the value of M2 shall depend upon the assumed value of lambda f. As per this clause, M2 shall be calculated as M2 equal to 0.02 into HW by Tf the whole square if lambda f is assumed as greater than 0.5, otherwise it shall be taken as a 0. Clause 6.4 will provide us the ways to calculate the parameters lambda f, FCR and psi f, according to which lambda f is calculated as lambda f is equal to square root of Ly into Tw into Fyw by FCR, where FCR is given by FCR is equal to 0.9 into Kf into Tw cubed divided by HW. And finally, the reduction factor psi f is equal to 0.5 by lambda f, and this shall be taken less than or equal to 1.0. In order to have a better understanding of the various design criteria discussed in previous slides, let us go through a simple design example. So the sample problem is a simply supported laterally restrained beam of a span 6.5 meter is subjected to a maximum design moment MED of 539.5 kN meter and a design shear force VED of 269.5 kN. The shear VCED at location of maximum bending moment is equal to 62.5 kN. The uniformly distributed load for SLS verification can be taken as 30 kN per meter. Verify the capacity of section 533 by 210 by 92 UKB in S275. So this is basically a capacity verification problem. You are given the section designation as well as the material grade and all the design actions. So first you have to list out all the design action values. Maximum design bending moment MAD, that's equal to 539.5 kN meter. Then the VED, which is the maximum design shear support, equal to 269.5 kN. And the maximum design shear measured at location of maximum bending moment VCED equal to 62.5 kN. And the unfactored load, that's a uniformly distributed load required for the serviceability check, W equal to 30 kN per meter. The beam span L equal to 6.5 meters. Span to deflection ratio, this is assumed as 360, but it is not listed in the problem. For the given cross section, I have listed the various section properties like the depth, width, web thickness, flange thickness, root radius, and calculated values of the depth between the flange fillets, second moment of area about the major axis, plastic modulus about major axis, as well as the cross sectional area. Okay, now start with the material properties. Modulus of elasticity E and the yield strength of Y. In our case, we have used S275 grade steel for which Fy is 275 MPa. Partial factors of resistance, gamma M0 and gamma M1 both are taken as 1. And here we are making some assumptions on some other miscellaneous data, that is length of stiff bearing on the flange, which is the length over which the support reaction is distributed to the flange SS as 50 mm, and the location of this stiff bearing from edge is assumed as C1 equal to 0. Now we need to do a calculation for the cross-section classification. So we calculate the factor epsilon, that is square root of 235 by Fy. In our case it works out to be 0.924. We calculate the outstanding compression flange CS 86.9 mm and obtain the ratio C by TF, which works out to be 5.571. Obviously this is less than 9 into epsilon, so the flange class type is class 1. Therefore flange is class 1 under compression. So we start making the calculations for web also. The ratio d by tw for the web is calculated to be 47.178, and this is less than or equal to 72 epsilon. Therefore we conclude that web is also under class 1. Therefore the entire section in our case is class 1 under bending. Now we need to make a verification whether shear buckling is to be carried out or not. In our case, the depth ratio calculated for the web H minus 20F by TW works out to be 49.693. This is less than or equal to 72 into epsilon by eta. Therefore, we conclude that the shear web buckling is not required in the present case. Next is verification for shear resistance. Here we need to obtain the shear area ratios AV1 and AV2 as per AC3 and obtain AV as the maximum of AV1 and AV2. In our case, AV is worked out to be 5.724 into 10 raised to 3 mm square. Now the design plastic resistance VPLRD is calculated as AV into Fi by root 3 divided by gamma MO. Substituting various values, we obtain VPLRD as 908.75 kN. So we conclude the design shear resistance VCRD will be equal to the plastic shear resistance, that is VCRD equal to 908.75 kN. Therefore, the shear capacity ratio, which is VED by VCRD, is equal to 0.297, As this is less than 1, we can say that the shear capacity verification is satisfied. Next, we will go for verification for bending resistance. Before performing this check, we need to find out whether a reduction check is possible or not for the bending capacity depending upon the value of the maximum shear force recorded at the location of maximum bending moment. In our case, BCED is less than 0.5 times the plastic shear resistance. Therefore, such a reduction check is not required. The plastic resistance MPLRD is equal to WPLX into Phi by gamma MO, and this works out to be 649 kN meter. Our calculations shows that the section is a class 1 cross section. Therefore, the design moment of resistance will be the plastic resistance. Therefore, MCRD is equal to 649 Newton meter. So we have the moment capacity ratio, which is 0.831, that is less than 1. Therefore, the moment verification is also satisfied. Okay, now we shall go for the verification for resistance of the web to transverse forces. As already discussed, this shall be done as per EN 1993-1-5. The objective of this verification is to check the capacity of the web at the bearing level. So first we shall proceed for the calculation of the buckling coefficient Kf, which is obtained as SS plus C1 by HW into 6 plus 2, and this works out to be 2.598, and this is less than 6. Next we shall go for the computation of the effective length LE, which is obtained as LE1 is equal to Kf into E into TW square divided by 2 Fy into HW, and EC3 says this shall be limited to SS plus C1. So we have LE obtained as 0.05 meters. Now we shall proceed for the calculation of M1 and M2 as per equation 68 and 69. Please remember that the value of M2 depends upon the assumed value of lambda, which shall be corrected if required later. We shall go for calculation of M1 and M2. In our case, M1 is calculated as FIF into BF divided by FIW into TW, that is M1 equal to 20.723. Remember that the calculation of M2 depends upon the value of lambda assumed. In our case, we assume that lambda is greater than 0.5. Accordingly, M2 is calculated as M2 is equal to 0.02 into HW by TF the whole square. So we obtain M2 as 20.702. Now we go for the calculation of Ly as per equation 611 and 612 and obtain Ly1 as 0.15 meter and Ly2 as 0.15 meter. Accordingly, the final value of Ly will be the minimum of these two values, that is 0.15 meters. Now we need to verify whether the lambda f assumed is correct or not. So we shall proceed for the calculation for FCR, which is 0.9 into Kf into TW cubed divided by HW, and this works out to be 1008 kilonewton. Now we proceed for the calculation of lambda f, that is the square root of Ly into TW into YW, this divided by FCR. This is equal to 0.644, and this is greater than 0.5 as per our assumption. Therefore, no modification is required. So now the reduction factor for effective length psi f is calculated as 0.5 by lambda f, which works out to be 0.777 in our case. Therefore, the effective length for resistance L effective is calculated by multiplying psi f with Ly. So in our case, L effective works out to be 0.117 meters. From L effective, we now go for the calculation of design resistance of the web to transverse force using FRD is equal to FIW into L effective into TW by gamma M1, that is FRD is equal to 324.32 kN. So the web capacity ratio in our case works out to be 0.831. Therefore, we conclude that the web has sufficient capacity to resist the transverse forces. So the final check is the verification for serviceability limit state. We compute the maximum deflection in the beam under service loads, that is under uniformly distributed load, and this is obtained using the very standard formula 5WL raised to 4 divided by 384 EAX, and works out to be 6.015 millimeters. So the permissible deflection we assume as L by deflection ratio, that is 18.036. So the deflection check shows that the calculated deflections are very much less than the permissible ones. Therefore, our section passes the verification for serviceability as well. So to conclude, we say that the assembled section satisfies all the verification checks outlined in EC3, therefore is acceptable.